Okay, just let me share the slide here. Just to comment a little bit the waveform for the third harmonic injection that I explained yesterday. Okay, these drawings are much better than mine, of course, so it can be a little bit easier to follow the reasoning about the third harmonic injection we made yesterday. On this part of the slide, you can see that there is a situation in which you compare the triangular waveform in the modulator, and this control voltage is the sum of a component at frequency f1, the only harmonic that I want to get at output, plus a third harmonic, and that gives this yellow behavior. Okay, as you can see, this plot shows the situation in which the component at frequency f1, the dashed blue lines, which is a sine wave at frequency f1, has exactly the peak value which is coincident with the peak value of the triangular waveform. In that second plot over there in the bottom of the slide, you can see a situation in which the yellow curve, which is the summation of the first and the third harmonic of f1, reaches the maximum possible linear operating range. Okay, why? If you operate in this specific situation, the component at frequency f1 exceed, okay, in amplitude the dynamic of the triangular waveform. And this is exactly the goal of using a third harmonic injection. So compress the overall dynamic of the control voltage in order to remain inside the linear operating region, but make it possible to have just the fundamental a little bit higher in order to extend in amplitude the linear control of the peak value of the control voltage, fundamental component of the output. Okay. Let me just look at this plot here, because this plot summarizes exactly the final results of our third harmonic injection. Okay, in this case, you can see that computation that we made are basically performed in order to get the maximum exactly at 60 degrees of the waveform, frequency f1. So here you can get the maximum. Here you can have a flat derivative versus this angle here, and this is only made possible when the amplitude of this third harmonic injection is 1/6 of the fundamental dashed line here. In that situation, you are able to maximize the fundamental component, and in this situation you can get exactly VD as a maximum value, okay, with an increase in the amplitude of about 15% with respect to the standard sine wave pulse width modulation. Okay, so look at these waveforms that are much better than mine, so you can compare what I said yesterday. If you have a question, I can answer. I have to share this waveform. I have to say if you hear me well, because here I have some warning about the audio. Are you hearing me? My voice is clear? Okay, good. Okay, so false alarm here. So let me consider another topic, which is called the space vector modulation of three-phase inverter. Sometimes you can find acronym SV pulse width modulation. Okay. So up to now we learned that in order to get a pulse width modulation behavior of the bidirectional converter, you need the comparison between a triangular voltage and a control voltage. Okay, by the comparison, the result of this comparison made possible to generate the unit switching function that command the switching status inside the converter. Space vector modulation is a technique that make possible to generate a pulse width modulation behavior. So at the end, you can have the standard behavior of pulse width modulation, but without the need for comparison between a triangular waveform, the carrier waveform inside the modulator, and a control voltage. Typically, this kind of modulation can be done totally in digital form. So you can find, say, application when you have digital control of inverters, three-phase inverters, and the algorithm for the space vector modulation can be stored into memories in say microcontrollers, microprocessors, or FPGA, DSP, etc. Okay, because it can be totally digitalized. Uh, Another thing that we learned about looking the pulse width modulator standard, the sinusoidal pulse width modulator for bidirectional converter, is that the control voltage say generates switching function that commands the leg, each of the legs that you can have in a bidirectional converter or three-phase inverters. Okay, there is a control voltage for any of these legs, for example, in three-phase inverters. Space vector modulation generates this behavior without looking at this specific leg for the inverter, but controlling totally the inverter are they were, say, as they are a unique entity to be controlled, okay, without, say, separating the activity for leg A, leg B, leg C, as we done for a sinusoidal pulse width modulator. Okay, so it's a say specific control technology that now is, say, most of the time is employed for three-phase inverters, and at the end you can obtain, as we can see in this lecture, say the same amplitude, the same variation that we can get by using the third harmonic injection. So we will be able to increase by 50% more or less the amplitude of the fundamental frequency component of the output voltage, the line-to-line voltage, and with specific arrangement of this technology, this technique, you can also shift the high frequency component higher than the frequency F1 at much higher frequency than that you can have for sinusoidal pulse width modulator. So seems to, say, have only say a very large number of pros, and with respect to the sinusoidal standard pulse width modulation. Okay, so it increases the linear operation region by getting the same result with total harmonic distortion, and also you can get some advantages in, say, in terms of high order harmonic in the output spectrum of the line-to-line voltages. In order to understand which is the core of these modulation techniques, we have to start by some not so complicated, I have to say, very simple math. That is the Park transform. What is the Park transform? First of all, we have to consider that the Park transform applies to any set of variables that are arbitrary variables, independent variables, real variables, and dimensionally homogeneous. The Park transform applies to a set of, let's say, three variables. Okay, so let's consider three variables. For example, let me call them UA, which is a function of t, ub of t, and uc of t. Okay? Suppose that you have this set of variables that are arbitrary, independent, real, and dimensionally homogeneous. And another important characteristic that they must have is that their sum must be 0. Okay, if you have these, say, characteristics, and their sum is 0, these variables can be represented in a bidimensional planes by using this transformation. So I can represent these three variables having these characteristics as a vector in a bidimensional plane. Okay, this vector, which is u, is called space vector, and this space vector is a complex vector. Okay, and this transformation includes c, which is a constant, and gamma here, which is 2/3 of p, or 120 degrees. Okay, so by using this Spark transform, we'll be able to, say, have this kind of transformation by which three variables can be represented in a complex plane. Okay, and in this complex plane, you have, say, this complex vector, which is called the space vector. Okay, and the definition of this transformation is provided by this expression here. Just to give you an example, I have this complex plane, which you have the imaginary axis, and you have here the real axis, and suppose that the time t is fixed. Okay, if the time is fixed, then you can have this vector, for example, having an absolute value indicated in this way, and then you have, let's say, an imaginary component, let me call it u beta, and a real component, which is u alpha. Okay, so the space vector is a complex quantity that can be decomposed into the real part, pu, and imaginary part. Okay, so let me also call in this way real part of u plus j imaginary part of u. Then this real imaginary part can be also indicated with a specific name. For example, the real part is indicated as the direct component of the space vector, and the imaginary part is called the quadrature component of u. Okay, so direct and quadrature component, the real and imaginary part of this space vector. So this angle here is simply the given by the arctangent of the imaginary part with respect to the real part. Let me just provide a very simple manipulation on this expression here, okay, to find out the real and the imaginary part of the space vector in terms of u alpha, ub, and uc. So in order to do this, I should use the Euler's formula that provides the representation of an exponential function like this in terms of trigonometric function like sine and cosine. So if I use this formula here and apply this formula on this representation of the space vector, okay, I get these steps u, which is c, that multiplies ua of t plus ub as a function of t. Here you have exponential of j gamma, and so exponential of j gamma is provided by cosine gamma plus j sine gamma, and then you have uc as a function of t multiplied by, you have an exponential function which is e 2j gamma, and so we have cosine of 2 gamma plus j sine 2 gamma. Okay, remember that now gamma is 120 degree, so we can have the, say, we can compute cosine gamma or cosine 2 gamma, etc. For example, for cosine gamma, it means cosine of 120 degree, and so on. Here you can get minus 1f. The sine of 120 degree is square 3 of 2. Cosine of 2 gamma is again negative 1f. Sine of 2 gamma is negative square of 3 divided by 2. So the space vector is the multiplication of the constant c, and then you have ua of t minus 1f ub plus j square 3 of 2 up minus 1f uc t minus j square 3 over 2 uc. So we can also rewrite separating the real part from the imaginary part. So you can have ua of t minus 1f ub minus 1f uc and then you have the imaginary part. So you have c here minus c, and then you have this plus c, this part here. ub, and then this part here, which is negative square 3 2. So this is exactly direct plus j quadrature component. So this is u alpha, and then you have put c j c here This is the U beta. This kind of computation, this result that comes out simply considering the Euler's formula and then separating the real imaginary part can also be represented in terms of, let's say, the matrix form. Okay, so we can have U alpha and U beta that are given by the multiplication of the constant C by, let me put here the vector UA, UB, and UC. And then you have 1, negative 1F, negative 1F, uh, 0, square 3 over 2, negative square 3 over 2. Okay, so this coefficient comes directly from, say, the computation that I had before. Okay, we have 1, negative 1F, 0, and square root of 3 over 2, negative square root of 3 over 2. So this is the metric representation of this kind of Park transform that make possible to convert a, say, system which we have 3 variables having specific features by a vector in a complex plane, and U alpha and U beta are the real and imaginary part of this vector. So we can say that this kind of transformation makes possible to, say, given 3 variables, U, A, U, B, and U, C, that are basically 3 variables. So we can say that there are 3, say, phase variable into a system which we have just 2 variables at the output that are the direct and the quadrature component. Okay, this transformation has a transformation matrix, which is exactly the transformation, the matrix that I computed now. Of course, also there is also the possibility to get the inverse transformation. Okay, from a 2-phase complex plane, I can pass to a description by using 3 variables that are independent, real, etc., by using the inverse transformation. So this is the basic idea. Okay, so to use this transformation to move from a system in which you describe you have a description by using 3 variables in a system where you use just 2 variables. Okay, so 3-phase, 2-phase systems. Let's have an example of application of this transformation. Okay, these examples are, say, not just random example, but will be used in the following this explanation. Okay, so suppose that, so example. Now let's consider some specific 3-phase variables, okay, UA, UB, and UC that are specifically defined. For example, suppose that UA is given by a cosine variables like this one, which you have a peak value, which is U with this hat on top, cosine omega t. Then the variable UB t, which is U cosine omega t minus gamma. So it's the same as UA, but you have a phase shift of gamma, and gamma is 120 degrees. UC t, which is U, big value, cosine omega t minus 2 gamma. Okay, now the waveform is always the same, so the 3 waveforms have the same peak value. The 3 waveforms have the same frequency, but they are phase shifted by 120 degrees one from the others. Okay, so this is a 3-phase symmetric systems. I don't know if U is a voltage, is a current, or whatever other physical meaning. Okay, for now they are just free variables, not well specified. Okay, it's a function. Consider that we have to prove that this kind of free variables has exactly the specific feature that we need for the path transformation application. Okay, so they need to be, let's say, arbitrary values. So this is the case. Independent. No, suppose that UA, UB, and UC are independent. Real. Say, let's suppose that they're real. Dimensionally homogeneous. For example, they can be whatever, 3 voltages if you want, 3 currents. Okay, and the summation of the 3 must be 0 for any t. So this is the case. If you have a 3-phase symmetric systems like this, for example, it means that you have this can be UA, a 360 degree, 180, so basically 120 is here. You have UB, and then you have UC that starts here. Something like that. Okay, you can find a better plot of a 3-phase system in the slide. Maybe later I can switch to the slide to say look at better drawing than mine. But basically the idea is that if you consider any instant of time, the characteristic of a 3-phase system that you sum up the 3 variables, you get 0. Okay, for example, let's consider what happens at time at the angle 0. Okay, you have this quantity here. My drawing is not perfect, but this quantity here is exactly the opposite of this one, and then this one is 0. So the summation here is 0. If you look at this interval, this angle here, you can get the sum of these 2 identical quantities, and it occurs that the summation of the 2 equates the peak value you have here. Okay, then you have another situation here that is the same that I examined at the beginning. So you have 2 quantities that are, say, opposite in values, they cancel out each other, then you have 0 here, etc., etc. So the sum of the 3-phase variable is null. Any instant of time I consider. So we can apply the path transform to this set of variables, okay, because they have the characteristic we need. We search for applying this transformation, okay? So remember that the transformation is U constant C, UA plus UB exponential of J gamma plus UC J to gamma. Okay, here. So just replace for each of these variables into the space vector representation. And so you have U pick cosine omega t plus U pick cosine omega t minus gamma exponential j gamma plus U pick value cosine omega t minus 2 gamma e j 2 gamma. Okay, so I put UA, UB, and UC looking at my variables 3-phase systems. Okay, so let's consider that cosine of a variable, I don't know, y, can be also written by using exponential terms like jy plus e negative jy. Okay, so we can use this transformation for the cosine, and so we can find out that u is c. I can put outside also the big value, which is always the same. Cosine, the first term is this one, cosine omega t. So this is 2 omega t plus minus j omega t. Then you have the second, which is cosine omega t minus gamma, and then you have the exponential. And then you have the j omega t minus 2 gamma plus the exponential of negative j omega t minus 2 gamma and then j2 gamma. Okay, so I simply develop all the trigonometric cosine function into an exponential function. Let me just manipulate a little bit by performing the multiplication between, say, the exponential you get in this long expression here. So you can have 1f e j omega t plus 1f e negative j omega t, which is the first part. Then the second one is 1f. Okay, if you now multiply this one to the first exponential, okay, you can get that this one is e j omega t e minus j gamma. When you multiply by j gamma, these terms disappear. Okay, you have just one. So this is 1f j omega t plus 1f. Now you have exponential negative j omega t multiplied L to j gamma. Okay, because now we have here you have e minus j omega t multiplied by plus j gamma. Okay, so when you multiply by the exponential, you can get exponential elevated to 2j gamma. The third part here is basically the computation is performed in the same way. In the first case, you have this exponential that multiplied this, the first exponential, then you have this part that disappeared, so the multiplication gives 1. So you have e j omega t plus 1/2 e negative j omega t multiplied e j4 gamma. Okay. Check my stats because it would be possible that I miss something. Okay, I say choose for the wrong sign, etc. So pay attention. So you have CU. Now, just sum all the similar terms. For example, I have here 1f exponential of j omega t. Then I have another one here, and I have another one here. So I have 3 divided by 2 exponential of j omega t plus, for example, I can have all these exponential remaining part. Let me put here 1f because they have 1f in common. Okay, 1f e negative j omega t, which is the first one. Then I have the second one, which is negative j omega t minus 2 gamma. And the third one, which is exponential of negative j omega t minus 4 gamma. Okay. So we found out this expression, this exponential function. Okay. Look at this parentheses, the square parenthesis here, the content of this parenthesis. You have 3 exponential, complex exponential function. One is, let's say, j omega t. The other one is the same, but is shifted by 240 degree. And the other one is the same, but is shifted by 4. Okay, so is 480 degree. So let's have a plot of these 3 functions here, just on a complex plane. Okay, suppose that you have here the imaginary and the real part. It means that you have a representation of this exponential here, which is an exponential which has, say, a behavior like this one. Is an imaginary plane, okay, is in a pure imaginary quantity here, and then we can plot in this way. Then you have another one which is the same amplitude, okay, so the absolute value is exactly the same, but it is shifted with respect to the first one by 240 degrees, so it is here. The length of this vector are the same. And then there is another one which is, say, same absolute value, but it is shifted by 240 degrees. Okay, so here is 240. Then you have another one which is 480. So it is here. Basically, there is a triple, say, vector representation. Okay, but if you want, they are summed up each to the others. So when you sum up these 3 vectors representation, you get 0. Okay. Basically, this is another. So this quantity here in this parenthesis is always null for each t. Why? Another view of see the same result is that here you have a, say, 3-phase representation. Okay, this 3-phase representation is not composed by sine wave that are shifted by 120 degrees, but by 240 degrees. But basically, you have the same. And what happens for any time instant where you have a 3-phase system, that the sum of this waveform is always null for each time instant. So the representation, the complex plane, is given by the exponential function. Each of them represents effectively a component of this 3-phase system. When you sum up, you can get 0. So this parenthesis is not present, and at the end of this Park transformation, you can have that U, the space vector, is C, that multiplies the peak value 3 divided by 2 E j omega t. So this is the representation that you have for that 3-phase systems UA, UB, UC that you have at the beginning. Look at this space vector. Okay, we can represent this space vector in the complex plane. So you have the real axis, the imaginary axis. Okay, we transform our three-phase system into a vector, and this vector depends on t. So this vector is a rotating vector. Okay, you have the amplitude of this vector, so the absolute value, which is c u multiplied 3/2. This is the length of this vector, but then this vector rotates in counterclockwise, anti-clockwise direction, okay, in this plane. For example, when omega t is null, okay, when omega t is null, you have just this real vector. When omega t is 90 degree, you get the pure imaginary vector, and etc. etc. You have omega t p, you get another real negative value. When you have omega t 3/2p, you are here, negative pure imaginary value, and then when you have 2p as omega t, you get here. So by using the Park transformation, mathematically, we found out that the space vector for these three-phase systems, that can be voltages or currents or whatever, can be represented in the space plane by a space vector which has a specific amplitude, and this is the amplitude, the magnitude of this vector rotating with a speed which is omega in this complex vector. Okay. Rotating space vector. Let me just choose a value for this constant c. Okay. Basically, you can find two different way to choose the value for this constant c. One lead to what is called the space vector amplitude invariant. So this kind of definition means that I'm choosing c to be exactly 2 divided by 3. In this way, the space vector, the space rotating vector, is exactly u e j omega t. Why this selection is called space vector amplitude invariant? Because the amplitude, so the magnitude of this space vector here, is u hat, which is the same amplitude of the three-phase variables we had at the beginning. Okay, here. So this means that we are not changing the magnitude of the variables. This is space vector amplitude invariant selection for the C. And this is the choice I will use from now on. Okay, there is another possibility for choosing C that provides you space vector power invariant. That means that the power provided by the three-phase system at the beginning of this analysis would be the same of the power provided by the rotation of the space vector in this plane. Okay, but this is a different choice that is not that I will not use anymore in this explanation. So let please see, which is 2 divided by 3, giving this expression for the rotating vector. Let me consider another example. Okay, so the first example shows that when you apply the Parks transform to a three-phase system, then you get a rotating vector. Okay, this is very important for what I'm going to explain in a moment. The second example, want to apply the Park transform to a three-phase inverters. Okay, so let me consider ideal schematics of a three-phase inverters, in which you have the voltage VD, and then you have the classical three legs. And so you have the node A, the node B, the node C. Remember that this is switch S1, S3, S5, S2, S4, S6. It is possible that yesterday, when I explained the square wave three-phase inverter, I exchanged S4 and S2 in my description. Okay, I have this impression, but anyway, it's not a problem. Okay, let me choose this definition for the switches inverter. Of course, I put here ideal switches that you can have transistor. Then you have the body diodes. Okay, always remember that the standard implementation. Okay, you know that we have the unitary switching function. Okay, that logic function, so that can have 1 or 0 values. That can be useful, that can be employed for defining the status of the switch. For example, when the unitary switching function is 1, it means that the switch to which this function is applied is on, is closed. When the unitary switching function is 0, it means that the switch is open, okay, is off. So let me say that Qk is a specific unitary switching function in which k can be from 1 to 6, because now we have 6 switches. And basically Qk, it is 1 if the switch Sk is on, or is 0 if the switch Sk is off. Q1 equal to 1 means that this switch is closed. Okay. We need to know what is the value of Q4, but basically we must remember, and it is always something that we have to remember, that is not allowed to have two switches in the same leg both on simultaneously. Okay, S1 and S4, for example, should act in a complementary way. When S1 is on, S4 is off, because I don't want to short circuit the voltage VT. It means that you destroy your inverter. So Q4 is not something that I have to say define, because it's completely defined by having chosen Q1, which is equal to 1. Okay, so Q4 is simply 1 minus Q1, okay, by definition of complementary reaction of the switches. So it means that you have 6 variables here, okay? These variables, Qk, are 6 because you have 6 switches, but just 3 of them are independent. The other 3 depends on the other function of the same leg. Okay, for example, Q4 depends on Q1, so it is not dependent. So we can choose, for example, Q1, Q3, and Q5 as independent variables. So that means that Q4, Q6, and Q2 depends on these 2 variables here. Okay, so let's consider. Of course, you can have different combination of the switch. Okay, let's start by considering one of these possible combination. For example, let's consider what happens when Q1 is 1, when Q3 is 0 and when Q5 is 0. Okay, so these are independent variables. I can choose, for example, this specific combination independent and one from the other. Let me consider what happens in our inverter having this specific, say, combination of the unit switching function. It means that Q1 is 1, so this switch is closed. Q3 is 0, so this switch is closed. Q5 is 0, so this switch is closed. Okay, this is exactly the schematic representation of this combination. So let me have a look of the line-to-line voltages of this inverter. For example, what is the voltage VAB? But VAB is given by the voltage VD. What happens to the voltage VBC? The voltage VBC is null because the two low side switches are closed, so we have no voltage. VCA, which is the voltage that you can have here, the voltage VCA is negative VD. Okay, so we have these three voltages. They are dimensionally homogeneous. They are three voltages, so of course. They are independent, exactly. They do not depend one from the others. They are, the sum of these three variables is null, of course. VD plus 0 minus VD is null. They are real. They are real because they are real voltages. So we can apply the Park transform to this set of input variables. Okay. To VAB, VBC, and VCA. Remember that we can have the switching function. Let me call this switching function V1. The switching function, the space vector, the space vector obtained by applying the Park transform. Let me call V1. This is C, so 2 divided by 3 by our space vector independent amplitude invariant definition. Then we have the matrix transformation, which is 1, negative 1f, negative 1f, 0, square 3 over 2, negative square 3 over 2 of the three variables. The three variables are VAB, VD, VBC, 0, and VCA, which is negative VD. In that way, I can find out the real and the imaginary part of the space vector V1 corresponding to this specific combination of the switching function. Okay, so this is V1 alpha and V1 beta. We can say V1 alpha, so the direct component of the space vector is VD minus 1f VD multiplied by 2 divided by 3, which is the constant. So this is VD. The quadrature component is C, that multiplies plus square 3 of 2 multiplied VD. So it is square of 3 divided by 3 VD. So my space vector V1, which is related to Q1 1, Q3 0, and Q5 0 switching function, is VD plus J square 3 over 3 VD. You can also change this representation. This is in the real and imaginary part, but then this complex vector can be also represented in the exponential form. Okay, in order to get exponential form, you need to define the magnitude. So the magnitude of the space vector is the square root of the real part this is VD 1 plus J square 3 of 3, okay? So the real part is 1 plus the square of 3 multiplied VD. And this is 2 over square 3 VD. And then you can have the angle, which is the inverse tangent of imaginary part over the real part, and this is 30 degrees. So another representation for the space vectors is V1 2 divide square root of 3 VD exponential of J B6. Okay, so you can express in both the forms if you want. Okay, exponential representation, or say real and imaginary representation, which is this one. Your choice. Okay, so I use as an example the three-phase inverter. I have a specific combination of the switch. Okay, I choose, say, this one, and I find out a representation. Okay, this representation, this space vector, is not a rotating space vector. Okay, as you can see here, there is no time in this expression. This is just a vector which is, say, fixed in space. Okay, so this is not rotating, something that we cannot move. This combination that I indicated here as an example, which is 1, 0, 0, the sequence 1, 0, 0, starting from Q1, Q3, and Q5, exactly in this order, is called the switching words. Which is 1, 0, 0. Okay, no, my switching word is 1, 0, 0, meaning that from the left to the right, I have exactly Q1, Q3, and Q5. So 1, 0, 0 is for the leg A, B, and C. Okay, in this order, A, B, and C. This is just one of the other possibility that you can have in this inverter. Okay, so let's explore all other possible combination. Okay, and if you explore all others combination, let me put here a table in which you have Q1, Q3, and Q5. So this is the switching word 100. Then you have VAB, VBC, and VCA. Remember VD 0, negative VD, and then the space vector representation, which is V1. It is 2 divide square root of 3 VD EJ B divided by 6. Okay, so let's have a look what happens if I choose this combination here, which is 1, 1, 0. So in this combination, I have 1, 1, 0, meaning that now this switch is open, but this is closed. Okay, 1, 1, 0. S1, S3 are on, and S2 is on. So, for example, VAB, the voltage between these two nodes is 0 because the two I-side switches are closed. VBC is VD because it's the voltage between this node and this one. And VCIA is negative VD because nothing changes with respect to the previous combination 100. So I have here 0 VD negative VD. The three variables here are exactly follow the same pattern, that they have the same characteristic of the previous VAB, VBC, VCA. They are real, they are independent, the summation is null, dimensionally homogeneous. So we can apply also for this case the path transformation. Okay, if you apply the path transformation, you can get a space vector which we can call V2, and exactly in the same way we did here. Okay, we can apply this transformation. Now this vector changes because it's 0 VD negative VD, so you can find different expression for the space vector. Okay, nothing new. You can apply this mathematical derivation, and you can find that the vector is 2 divided by square root of 3 VD E J P divided by 2. This is another fixed space vector, not rotating, but it's a different position with respect to V1. So let's go further with this combination. So it means that only S3 is on, then you have S4 and S6 which are on. You can get negative VD, VD null. Again, we can apply the space vector, space transformation in order to get V3, which has the same amplitude of the V1 and V2 space vector, but it has a different angle. 0, 1, 1. 0, 1, 1 means that you have negative VD, 0, and VD. You get a space vector V4, which has the same amplitude of the previous space vectors, but a different angle. Zero, 0, 1, 0, negative VD and VD, V5, 2 divided square root of 3, VD, E, J, 3 divided by 2, P. 1, 0, 1, you have VD, negative VD, and 0. V6 is 2 divided square root of 3, VD, E, J, 11 over 6, P. Then you have 1, 1, 1. It means that all the I-side switches S1, S3, and S5 are on. If you get VAB, this is null. If you have VBC, this is null. VCA is null because all the top side transistors are on. You can apply the path transform to this set of variables, of course, because the summation is always 0. They are independent variables, are real, etc. So we can get a V7 voltage, which is identically null. And then you have another combination, which is 0, 0, 0. Here, in which you have all the low side transistor on, so you get S4, S6, and S2 that are on, and so you can get again VABC, VAB, VBC, and VCA that are all null, that you have the vector V null, which is V0, which is null. Okay, so here you have 7 space vectors fixed in the complex plane, same same magnitude. Okay, the magnitude is 2 divided square root of 3 multiplied VD. But different angles. From these 7 space vector, you have, sorry, they are 8. From these 8 space vector, you have just, say, 6 that are not null. Two are null space vectors. There are these two one. The space vectors that are not null, they are called the active space vector. The two space vectors that are null are called exactly the null space vector. Okay? So this is the representation. So now we can plot these vectors in the complex plane. This is the real axis, the imaginary axis. So let's start with the null space vector. The two null space vectors lies at the origin of this plane. Let me put it this way. Here you have the vector v0 and the vector v7. They are the null space vectors. The combination here of the switching word is 0, 0, 0 and 1, 1, 1. Okay, these are the switching words for the two null vectors that are here. Then let's start with the space vector v1. v1 has, say, a magnitude, but has this angle here. This angle is exactly 30 degrees. So it is a vector switch word is 1, 0, 0. Okay, this is v1. Then you have another space vector, which is this one, okay, in which the amplitude is always the same, but the angle is at 90 degrees. So it is here. V2, which correspond to 1, 1, 0 switching words. So the difference here is 60 degrees. Then you have V3, which has this angle here. This angle is 5p divided by 6 is 150. This is V3, and this is 0, 1, 0 switching word. Again, you have here 60 degrees between V2 and V3. Then there is another one, which is V4, that corresponds to 0, 1, 1 switching word, that is shifted again by 6 degrees from the previous one. Then you have V5. V5 is exactly 270 degrees. This is 001 switching word. Again, you have 6 degrees from the previous one. And then you have another one here. V6, which is 101. Again, you have 6 degrees from the previous one and another 6 degrees from here. So the representation of the, say, active space vector is fixed in space. They are, say, separated by 6 degrees each from the successive. They have the same amplitude, okay, so they have the same length if you want. And then you have two null vectors that are at the origin of this complex plane. Let's have a 10 minutes break, okay, then we continues this discussion about this representation of the switch combination in the three-phase inverters, okay? 10 minutes from now. Okay, let's continue our discussion. Have you some doubts, questions about these computations, the way I obtained these vectors, something which is not clear, whatever? Okay. This is the representation in the complex plane of the 8 space vector that represents the line-to-line voltages of a three-phase inverters, okay, for all possible combination of the switch, the 6 switch that you have in this three-phase inverters, okay. Just some say random consideration about this space vector representation. First of all, we have 6 active vectors, not null vectors, that are separated by 6 degrees each from the successive. Okay, so for example, V1 is 6 degrees from V2, but is also 6 degrees from V6. So this means that my complex plane is divided into 6 sectors. Okay, so this is the sector 1, then you have the sector 2, the sector number 3, the sector number 4, the sector number 5, sector number 6. Okay, you have 6 sectors, and then these sectors has an angle which is 60 degrees. All these space vectors have the same amplitude, okay, which is 2 Vd divided square root of 3. And then you have 2 null vectors that correspond to these 2 switching words that are located exactly in the origin of this complex plane. Then let's have a look of the switching words related to each of these space vectors. Okay, so these are highlighted in this way. For example, V1 has 100. Remember, 100 means the sequence Q1, Q3, Q5. 100 and nearby vectors V2 and V6 are respectively 110 and 101. So there is just 1 bit of difference between the switching words of adjacent vectors. Okay, from 100, I have to change this second bit here to 1 to get into V2 space vector. From V1, I have to change the bit Q5 here just to get into this V6 space vector switching word. So each vector is, say, separated just by one bit with respect to the adjacent space vectors. And this is also true for the null vectors, okay? Because 1, 0, 0, which is the V1 vector, is one bit from the null vector 0, 0, 0, okay? You have to change this one to get V1. And it is, why this is not true for this one, okay? But any space vector is distant one bit for one of the two null vectors. Okay, for example, V6 is distant one bit from this one because you have to change this, or V2 is distant one bit from again 1, 1, 1 by changing the third one. Okay, so this is a specific characteristic that involve the topology of our inverter. What does it mean? That you have just one bit of separation between adjacent vectors. It means that you have to change the status of just say one leg of the inverter. Okay, so for example, for 1, 0, 0, which is this combination here, so you have 1, 0, 0, okay, and then you want to pass to move from V1 to V2, then you have to consider the second bit here, so the leg B. And then it means that you have to close this switch here and to open this one. Okay, so you have to switch to make the switch for that specific leg. Okay, you have to change the status of one leg. Of course, the separation in terms of bit, okay, means that you have to apply a switching action on that specific leg. But since the distance is one bit, means that you are minimizing the switching action, okay? For example, if we want to pass from V1 to V4, okay, which is the opposite side of the same plane, then you have to switch all the three legs. So you have to, say, in this situation, you have to, say, change all the combination of the switch. So it means that you have a higher switching action, okay? So distance of one bit minimizing the switches that are involved in the commutations, okay? Let me just answer the question. Marco Simonetti asked, the combination is similar to an half stepping. Half stepping means the stepper motor. You are talking about the stepper motor. The half stepping is the combination in which you excite one phase and then two phases, then one phase. You alternate the one and two phases. You are referring to that specific, say, operation. Is similar to that. I don't see any similarities here. Because you are saying that why you see this similarity. I don't see these similarities, okay? But the combination, I really don't see your point. I cannot see your point. For me, it's not the same. Because what does it mean that I am, say, exciting one phase and then two phases? This is not means that there is no similarities anyway. The question is, the answer is this one. There is no similarity and there is nothing to do with that case, okay? Anyway, here I'm not saying that you are activating one phase at a time. Pay attention, okay? The 1, 0, 0 is related to the switch that I'm closing or opening, okay? 1, 0, 0 means exactly that I'm closing S1 and the switches S3 and S5 are open, okay? So just looking at what happens to the legs. Okay, then in three-phase systems, I have to excite all the phases simultaneously. There is no phase which is not activated. Okay, we are in AC. The waveform is a little bit different. Okay, I just want you to understand this point. Maybe it can be some similarity, but I cannot see. Okay. So the fact that I'm selecting just one bit of difference means that I have to switch just one leg. Okay, and this in terms of, for example, power dissipation, dynamic dissipation is helpful. Okay, I don't have to switch, for example, passing from one vector to adjacent vector all the legs. I have just to change the position and the status of one leg. Okay, the other two are always the same position. They are not dissipating any dynamic power, for example. There is also a geometrical interpretation of this kind of representation. Okay, this is the space vector representation, but let me just to describe, let's say, the same, say, the result that I get by using this Park transform by using a sort of a geometrical representation. Okay, so let's consider a plane in which I have three coordinate axes like this one that are separated by 120 degrees each from the others. Okay, this is representing the voltage VAB, so the line-to-line voltage between the leg A and B. This is representing VBC, and this is representing VCA. Okay, so put on this plane the space vector V1, for example. Okay, just considering one, but the same happens for all other. So V1 is here. So let's put this vector with the magnitude, so the length of the vector, which I provided, which I computed before. And then also this angle here, which is, this is 60, so this is 30 degree. Okay, so this is 30 degree. So I put this vector in this other plane. And let's consider what happens to the projection of this vector on this coordinate axis, VAB, VBC, etc. Of course, we are this projection here. Okay, so we have this vector here, which is the projection of V1 onto VAB. Then I have the negative part of VAC, and then we have here the projection along this axis here. Sorry, the drawing is very badly, okay, because this is 30 degree and this is 120, so the difference here is 90 degrees. So this vector VBC should be orthogonal to this one. Okay, so yeah, so the projection of this red vector onto VBC is null. And the same angle here, this is 120, so this is 6 degrees. So 30 is exactly in between. So let me just something which is much close to the reality. Okay, V1 is here. This is 30 degrees. So this is the projection. Here I have another projection along this one. And this projection here along the VCA is the same of that you have onto VAB. Okay, so summarizing with this construction, the projection of V1 onto VAB is equal to the projection of onto VCA. The projection along VBC is null. Okay, so let me put on a bidimensional plane, let's say here, the space vector V1. So I have that, supposing that here you have, I don't know, that axis and time axis. The projection along VBC is null. So let me put here. This is the projection along VBC. I'm putting exactly the value of the projection of this vector. Then I have the projection along VAB, which is here. The projection along VCA has the same magnitude of that you can have along VAB, but it's negative because it occurs in the negative axis. So it is here. Okay, so we have these 3 points here. So this is VAB, VBC, and VCA. Consider what happens to the vector V2, for example. The vector V2 is vertical. Now there is no problem in drawing this. So what happens if I get the projection of this vector along these 3 axes, VAB, VBC, and VCA? For sure, I have no projection along VAB. So let me put another axis here, considering V2. Let me consider here an angle which is much, say, so this separation is 60 degrees, because between V1 and V2 you have 60 degrees. Okay, here you have 60 degrees. So the projection of V2 along VAB is null. So the projection that I put in red here now is null. The projection along VBC is the same, now the construction, that you can have along VCA. So you have something which is, let me put here, VBC is positive, so it is here. And the purple one is again negative, I don't know, somewhere here. Okay, so as you can see, there is an evolution of this projection, the VBC, for example, projection from this point to this one. There is another evolution from the projection of VAB to this another point VAB, and there is another projection here, another evolution of this projection from these 2 points here. I don't know what happens in between. Okay, I just looking at, say, specific discrete angular time, angular position of this vector. Okay, then you can get, this is for V2, then you can get V3, V4, etc. I just want to show you what happens if you replicate this drawing for all the 6 vectors. Okay, so let me just share the slides. Okay, so I just drawn V1 and V2 points, then V3, V4, V5, V6, etc. As you can see, the evolution of the vectors that you can have in these discrete 6 different angles, from starting from 0, 16, 120, etc., is that they track the evolution of a 3-phase voltage system. For example, VAB has this, the behavior here. So you have this point here, 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 and here. VBC, according to the construction, here, 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 etc., etc. So basically, you have discrete point that tracks this behavior. Okay, so this is another, say, interpretation of the same representation. In practice, the space vectors represent the line-to-line voltages values that occurs any 60 degrees in this way. Okay, so the sectors are exactly what happens in between these two fixed position. Okay, so the space vector are fixed and they describe exactly what happens any 60 degrees of this three-phase evolution of the line-to-line voltages. Okay, so this, if you want, this is a geometrical interpretation of what I already described in terms of park transformation. Let me just go again to the whiteboard, because now I want to stress the fact that we are in this condition. We have an inverter, a three-phase inverters, and depending on the combination of the switch, and then we have just 8 possible different combination of the switch, you can have 8 possible different values for the line-to-line voltages. Okay, they are exactly the position defined by the space vectors values previously described. What is the goal of any inverters, specifically of these three-phase inverters? To generate their output as line-to-line voltages a three-phase voltage system. Okay. Now I'm just considering what is the possibility that the inverter has to generate some specific discrete points in a three-phase evolution. But this is not the three-phase voltage system. Okay, we miss all the evolution that you can have in all the 6 sectors. Okay, according to my description, okay, the 6 vectors, the space vectors of the inverter just describe fixed position any 60 degree here, here, etc. Okay, but what happens inside the sectors is not defined. Remember also that we have a description in the space vector of a three-phase voltage system. Okay, remember this exercise, this example. Okay, what is the representation in the space vector plane of a three-phase symmetric system like this one? Okay, is a rotating vector. Remember our long computation is a rotating vector. So concluding this discussion, we have a rotating vector here that rotates in this direction, which represents the three-phase symmetrical systems. For example, the voltage VAB, VCIA, VBC over T for any time instant. This is rotating, is moving, okay? And then from the other side, we have an inverter, okay, a three-phase inverter that, depending on the position, on the combination of the switches inside the legs, can generate only fixed position that are those indicated by the space vectors, and that represents a specific discrete time interval. Okay, so the goal is to use the space vectors that represent, say, fixed positions to simulate, to synthesize the rotating vector. Because this is done, that is the goal of any inverter. Okay, using, say, some specific and discrete voltage to generate something which is, say, time continuous variable. Okay, so in which way we can do this operation? Okay, let's consider an example just to give you an overview of what happened. So let me redraw the complex plane and let me consider just the first sector, so V1, which is 1, 0, 0, and V2. One, 1, 0. These are just two possible space vectors, okay? And then you have inside the rotating vector representing the full sinusoidal three-phase voltage system. Let's suppose that, for example, but here is not important. Okay, let me just consider this representation here. Okay, so you have the sector number 1. Okay, in which way I can use space vectors, so the red vectors, to simulate, to synthesize the moving rotating vector? We have to consider the say combination of different vectors to synthesize the purple vectors. Okay, you know that by using any combination of two vectors, for example, okay, weighted by specific amplitude, okay, you can synthesize any other vectors. Okay, for example, if you use this combination, I don't know, here, okay, you can synthesize summation of these two provides you these third vectors. Okay, so it is possible, generally speaking, using any two vectors, any two space vectors, to synthesize another one in any position of the complex plane. Okay, but what happens here? This purple vector is rotating. So the main assumption that is made here to have the possibility to use the red fixed vector to synthesize something which is rotating, is moving, is that the rotating vector here has a velocity which is not so fast. So it means that we are considering the rotating vector almost fixed for vector combination, a space vector combination, fixed space vector combination. So the only possibility to synthesize something which is rotating by using something which is fixed is that the frequency of this rotating vector is not so huge with respect to, say, the operation that I have to perform. And what is the operation that I have to perform? I have to combine these two vectors, for example, in a sort of vectorial summation in order to synthesize something which is now I'm considering almost fixed. Why I have to consider V1 and V2? Because generally speaking, I can use any couple of vectors. For example, I can use V1 and I don't know, V4, which is here. Which has 0, 1, 1. But remember what I said at the beginning of this discussion. When you use two adjacent vectors, the switching word just has one bit of difference. 1, 0, 0 is one bit from 1, 1, 0. It means that I'm just switching the leg B. And this action, this operation minimizes the dynamic power dissipated by the switching action of transistors. Okay, so Theoretically, I can use V1 and V4 to synthesize as the purple moving rotating vector, but this involves the switching of three legs. And so this is something that increases too much the dissipation, the power dissipation. So in order to minimize the dissipation, to increase the efficiency, it is always convenient to use for synthesizing the rotating vector adjacent vectors, the vectors that are bounding the sector in which the rotating vector is moving. Okay, here the rotating vector is moving inside the sector 1. Okay, and so the vectors that bounds the sector 1 is V2 and V1. So in order to synthesize this vector, which is now in this sector, I use V1 and V2. What does it mean using V1 and V2? It means that, let me just represent again the ABC inverter legs, VD. This is which 1, 3, 5, 2, 4, and 6. Okay, so V1 is represented by the switching function 1, 0, 0. V2 is represented by 1, 1, 0. Okay, so this means that I have this is closed and this is closed, and then I am switching these two. Okay, because it's the only bit that is changing is that related to the leg B. This is the node A, this is the node B, and this is the node C. Let's suppose that I am in the specific situation in which the rotating vector is half between V1 and V2. So it's exactly, let's say, the angle here is the same angle that you have here. Is an example, okay? So this rotating vector is in between half position V1 and V2. Let me just consider a plot of the voltage VAB, VBC, VCA, so the line voltages for the two space vectors V1 and V2. Okay, V1 means that you have this switch combination, so VAB is VD. What happens to VBC? VBC is this voltage here, and this is 0, so it means that this is closed. Okay, so you have 0. And then you have VCA. VCA is this voltage here, and this is negative VD. Exactly the three voltages that we used for the derivation of the space vector. VD is 0, negative VD. And this is the situation that lasts anytime you have this space vector V1. Then you have the space vector V2. So what is the difference? That you have the same voltage VCIA, because these two legs are, say, the same as before, so the voltage VCIA is the same as before. The voltage VBC now is different, because now the switch is closed here, so VBC is VD. And the voltage VAB is null. Okay, this is the combination 0 VD negative VD, that is for characteristic of the status of the space vector V2. Suppose the time is switching between V1 and V2 in time. Okay, so I last for a time interval T1 in the status V2, sorry, V1, this one. Then I change after T1 interval to V2, and I stay there in the status V2, changing the V position of the switch for a time interval which is T2. And suppose that I make this operation periodically. So periodic, so it means that you have T2 here, 0, negative VD, etc. So T1 plus T2 represent our TS, our switching period. So supposing that I'm using V1 and V2 periodically in that way, okay, what you get after some periods is that you have this plot of the waveform, okay? But then you can get the average value here. And the average value of this waveform over a period, what is? VAB average value will be VD multiplied T1 over Ts. What is the average value of VBC? VBC has an average value over Ts, which is VD T2 over Ts. What is the average value of VCA? Now it's much more simple because this is constant and this is negative VD. Since my idea is to use V1 and V2, these two specific combination of the switch, to synthesize a vector which is exactly at half, say, this angle, okay, so it is 30 degree here and 30 degree to V2, is exactly in between, intuitively means that I have to choose T1 over T2. If I choose T1 over T2, so this two-time interval in which I apply the space vector V1 and the space vector V2 are the same, it means that this average value is VD half and it is VD half. Why this is negative VD? So let me put this value on my previous plot. Where are they? Here, of the line-to-line voltages evolution. Remember, I have V1 here and I have V2 here that represent exactly something which is, say, in discrete position. Now I use the average value obtained by continuously changing from V1 and V2 to synthesize something which is in between of these two discrete values. And I get something which is VAB, something which is similar and is equal to VBC. The average value here of VAB is the same of that of VBC, having T1 over V2. Okay, so I get something which is exactly here. This is the crossing point that makes equal VBC and VAB. And then I get something negative here, representing exactly VCA. So using a switch combination periodically, I have synthesized a position which is not possible to obtain simply by space vectors that are fixed, okay? So I use an average value in order to find out which is something in between. And this is exactly the midway position of the rotating vector. But pay attention, in order to do this, the space vector must not moving during TS. Because if I choose T1 or T2 according to the position, okay, if during TS the vector, the purple vector is, say, has changed its position, then this computation is not working anymore. They only works if for at least one period TS, the rotating vector is not moving. So it means that rotating vector must have a frequency, okay, which is much slower than the switching frequency. The rotating vector frequency much slower than 1/Ts. Okay, this is exactly what I saying before. Maybe it's not completely clear at that time, but here I think that should be a little bit clear. Okay, I have to say have this. I can apply this vectorial combination by using static vectors in order to synthesize something, but this vector I want to synthesize must not moving during TS. Otherwise, my computation fails, are not correct. But this condition that I just justified in this way graphically, if you want, is something that we already met in previous discussion. This means that what is the rotating vector frequency? Is the frequency f1 that I want to get from my three-phase voltage system at the output. The low frequency, the fundamental frequency component of the output. So this sentence here simply states that I have to choose a switching frequency, Fs, much higher than F1. That is exactly the condition that must be fulfilled anytime I want to use, say, this kind of converters to synthesize, to extract information, okay? In order to demodulate from, say, waveforms like this one, an average value, this is only possible by respecting Nyquist theorem, and that gives this condition to be supported. So this is exactly the same condition that I have for any kind of other application that are not space vectors, okay? Here is graphically represented, okay? Because I'm using vectorial summation representation for, say, synthesize something that is, let's say, moving. So it is quite understandable that if I want to use these two vectors, I want to represent the purple one. This purple one should be, say, held in that position for at least TS for that computation to be whole, to be valid. Okay. Have you questions about this procedure, this method to explain this combination? So what the inverters can generate are just these rectangular waveform here. Depending on the switch combination, the only thing that he can do is to apply this kind of rectangular wave. Of course, we can average it. We can demodulate it, find, say, the fundamental component. And the fundamental component is a sine wave rotating along the complex plane. Okay. So this is an example that gives you, say, an idea of what is the time constraint for applying a space vector and another one, okay, v1 and v2. Now the space vector is exactly in between, so I can use t1, which is equal to t2. So the time interval in which I apply v1 is the same time interval in which I apply v2. Of course, if I have to, for example, synthesize the vector is moving, so another time instant the vector is here, okay, is rotating, change its position. So as you can see here, this vector, the second one, is much closer to v2 with respect to v1. So if I want to synthesize a vector which is closer to v2 with, say, respect to v1, then means that I have to apply v2 for a longer time interval. Okay, so for example, for a rotating vector closer to v2, it means that VAB should be something like this: T1, T2, etc. VBC is this one, and then VCA is always constant. Like this. Okay, so again, T1 plus T2 is our switching period, but now what happens to the average voltage, average value? VAB average, which is VD multiplied T1 over TS, is less than VD over 2. While here VBC average value, which is VD T2 over T1, is higher than VD over 2. Okay, so it means that the voltage VAB here, the average value, is less than the average value of VBC. And if you look at this plot here, means that you are, say, synthesizing something which is, I don't know, here, which the red curve, the VAB has an average value which is less than that of the VBC. So we are synthesizing something which is closer to the V2 vector. Okay, so T1 and T2 must be chosen according to the position. The only thing that must be clear then during TS, the vector should be, the rotating vector should be fixed in one specific position. So the rotating vector free frequency is much less than the switching frequency. TS is the switching frequency. By using this, say, operation, this procedure that I explained by using this example, basically graphically, you should understand that T1 and T2 play an important role in defining the, let's say, position of the vector. Okay, by choosing T1 and T2, I can synthesize, say, exactly the position. Okay, for example, T1, which is equal to T2, means that I'm just synthesizing something which is exactly in between V1 and V2. If I choose T2 larger than T1, then I'm something which is closer to V2, etc. But what about the magnitude? If I want to synthesize this vector, okay, in one position, or in the same position, I want to synthesize something which is, say, as an higher amplitude, because remember that I want to basically use the inverter to generate a three-phase AC voltage system, but in which I can modulate the frequency, F1, and the amplitude. Okay, so what happens if I want to synthesize something which is bigger, or say little, if you want? Using T1 and T2, I can just synthesize, say, something. I can choose the orientation, okay, the position, but not the amplitude. In which way I can modulate the amplitude? To modulate the amplitude of the rotating vector, we should use the null vectors. Okay, so suppose that again I have the situation in which the rotating vector is exactly in between, in the middle. Of sector 1. So the first case I considered before. Okay, so it means that T1 must be equal to T2, when T1 and T2 are respectively the time interval in which I apply V1 and V2 space vectors. Okay, so let me just to redraw VAB for this case. VBC and VCA, which is always the same, is not of interest now. So I choose T1 and T2 to be exactly the same. Okay, now I can use another null vectors. For example, I can use the combination 0, 0, 0, which is the vector V0 here, in which VAB is null, in which VBC is null, and which also VCA is null. Okay, so if you want, let me just plot VCA because it changed. If you use this another interval, which is called, I don't know, T0, which I apply this other vector, and this vector is, let's say, 1 bit distant from the 1. So I can use, let's say, this feature to minimize the dynamic switching. Okay, I get 0 here. I don't know which is T0. T0, the width of T0 depends on the amplitude I want to synthesize. Okay, so I get 0 here, and I get 0 here. Now this is TS. Okay, TS is here. What about the average value? The average value now is for VAB is VD multiplied T1 over TS, of course. But now T1 is not TS divided by 2. So this is less than VD over 2. And VBC is VD T2 over TS. But since T1 and T2 are the same, this is also VD T1 over TS, which is the same of VAB, but this is less than VDF. And the average value here is another different value, which is negative. It's not important for now, but what happens is that I have that the two average values for VAB and VBC are the same. So I'm again in between. I am in between of the sectors 1, okay, because VAB and VBC are equal just, let's say, for an angle that is, let's say, in between the sector 1. But the amplitude is not the same as before. Depending on the value of T0, I can modulate the amplitude, the magnitude of this average value. Okay, so the null vectors are employed, are added as another possibility to, let's say, modulate the amplitude without changing the direction. Okay, the direction is only, say, defined by the T1 and T2 time interval in which I apply V1 and V2. They define the, say, position of the rotating vector. T0 is added just to, say, modulate the value, the magnitude, okay, so to have larger or smaller through phase at the output. So basically, we can say that the output voltage, the line-to-line voltage, the vector, is always synthesized by a vectorial combination in which you have V1 applied for an interval T1 over Ts, which is an average value, which V2, space vector V2 is applied a vector for time interval T2 over Ts, plus you have also the V0 here. Typically, for reasons that I want to explain later, even if one of the two null vector is enough for defining the amplitude, as I show in this graph here, typically for enlarging the efficiency of the systems, the two null vectors are employed. Not only T0, but is employed also V7. Okay, so V7, T7 over Ts. Okay, for that for efficiency reason, let's say, that I will mention later, two null vectors are employed, not just one. So use both the null vectors. And these expressions here represent exactly the vectorial combination that I have averaging the quantities during TS. Have you questions about this explanation of the procedure that is involved here? Have you questions? Problems? Something which is not clear? Is all is clear? So in this case, we can, I just reading the question, okay? So in this case, we can modulate also the amplitude of, exactly. This basically provides you a means by which you can have larger, so rotating vector, so longer if you want, or say smaller, okay? Because depending on the amount of the time interval t0 or t7 in which you apply the null vectors, then you can minimize or you can have the largest possible vectors. For example, if you do not use t0 here in this explanation, if t0 is not present, okay, and so you have the previous example I gave you, the voltage VAB average value and VBC average value is VD over 2, which is the maximum possible. Anytime you add T0 and T7, so for B7 null vectors here, you are reducing the amplitude. Okay, so the null vectors are employed in order to, let's say, modulating, but say reducing what happens without using them. Okay, so the maximum possible amplitude is when you do not have any T0 or T7. When you apply T0, T7, then you can modulate, reducing the maximum amplitude. Okay. So let me to formalize a little bit this discussion by giving you exactly the expressions for evaluating T1 and T2 as a function of the position of the rotating vector. Okay. What about other output harmonics? This is the continuing. So you are asking me what happens for the high order harmonics, but basically I'm filtering. Yes, I can mention this factor later on in this discussion. Okay, but basically, I'm using here a averaging method. Okay, so I'm taking the average over a period TS. So this involves a demodulation operation. That means that I'm low pass filtering the rectangular waveform, the red one, that I can get as a result of the application of the different space vectors. Okay, so this is exactly the same method that I have for all other inverters and let's say bidirectional converters. I have something which is not constant for example, in the TDC converter. It's not a sine wave. I have to filter out to consider the baseband content. Okay, so what the let's say the behavior of the high order harmonics, okay, here in this specific situation for the space vector modulation is very similar to that you can obtain for linear pulse width modulator, sinusoidal one. Even if this is not a sinusoidal pulse width modulator, even if this is not a pulse width modulator at all, basically, because you can avoid, say, the comparison between a triangular wave and a sine wave, the spectrum is more or less similar. And as a matter of fact, you can have even a better, let's say, spectrum with respect to that of a sine wave, in the sense that exploiting some specific symmetries, that I mentioned later in this explanation, maybe tomorrow, you will be able to reduce the amount of high order harmonics respect to the linear pulse width modulation. For example, why I have to add here the null state V7 in a situation in which the vector V null here provides the behavior I need. There is no need to have another space null vectors like V7 to get the same result. I have already V0. Why I have to add V0 and V7 simultaneously? Because these, let's say, make possible to have more symmetries in the spectrum, in the say in the waveforms, and Fourier likes symmetries in order to eliminate some harmonics. Okay, so this is just here using V7 and V0 for modulating the amplitude is a means by which I can reduce the harmonic content at a higher frequency. Okay, this is a possibility that I can exploit and that you cannot have in the linear pulse width modulator. So basically, you have the same output spectrum of the sinusoidal pulse width modulator. So remember F1, then we have a bunch of harmonics around Fs, intermodulation product, etc. But here you have the advantages that you can exploit symmetries in Fourier transformation to reduce a little bit harmonic content. So basically here the total harmonic distortion you can get is a little bit lower for certain specific case with respect to that of standard classical sinusoidal linear pulse width modulator. I hope that this answers your question. So I just want to formalize a little bit this discussion. So okay, question. Okay, thank you to you. Another thing that I want to stress here is that my discussion here is using V1 and V2 as space vector because the rotating vector is in its evolution is in the sector 1. When the space vector rotating goes into the sector 2, then I have to use V2 and V3. Okay, I have to combine these two vectors to synthesize the vector. And then when the rotating vector goes in the sector 3, I have to use V3 and V4. So the space vector, the status, the combination of the switch that I have to use to synthesize the rotating vector depends on the sector in which the rotating vector is moving. Okay, but for all the position, all the time, all the say time instant in which the rotating vector is in the sector 1, let's say here, 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 here. Okay, for all these positions, all the infinite position you can have in sector 1, I have to use V1 and V2. Of course, with different T1 and T2. Because T1 is equal to T2 only if the vector is in the position, in the middle position. Okay? When the rotating vector is close to V1, I have to use T1 higher than T2. When the rotating vector is close to V2, I have to use T2 higher than T1 to enlarge the average. Okay, so this is the rules. Then I have to change the sector. I have to change the space vector I'm using. So let's consider now in a more formal way, which is the relation between the position of the rotating vector and T1 and T2. So I want to compute exactly, I want to derive you, say, a expression, a formula by which you can compute T1 and T2, depending on theta, okay? When theta is exactly 30 degrees, so in middle of the sector 1, T1 is equal to T2. But for our other angles, how can I compute T1 and T2 exactly to provide, to synthesize that position? Okay, and this is the answer. So for that computation, I am supposing that rotating vector is inside the sector 1. So I'm using to synthesize it V1 and V2. It is not a limiting, say, hypothesis, okay? When you can repeat exactly the computation I made here for this sector for all other 6 sectors, yeah, you get the same results. But basically, I want to focus on this sector 1. So here you have the rotating vector. I don't know what is this position. Let me consider this position as an angle theta with respect to the vector 1. And theta can be anything from 0 to 60 degrees. This is the horizontal position. And so you know that you have here an angle which is P over 6, is 30 degrees. And you see also that this is P divided by 3, 60 degrees from V1 to V2. This is the position theta of this vector, okay? And what is the amplitude of this vector? But we can, let me just to consider the amplitude of this vector as a coefficient alpha that I don't know respect to Vd, okay? So this is the magnitude of rotating vector, while theta is the position with respect to V1. Alpha is a coefficient not yet specified, is a number. Okay, so I know from my previous expression that I have to use a switching frequency, a switching period, which is the sum of the time interval T1, in which I applied V1, plus the time interval T2, in which I applied V2, plus both the time interval T0 and T7, in which I applied the 2 null vectors, V0 and V7. Okay, in this way. So let me just consider which is the expression, the mathematical expression of the space vector V1. This is Vd, remember, real imaginary part representation, this one, okay, which is the space vector representation of V2. This is 2 divided square root of 3 j Vd. We computed these 2 expressions before, okay, when we have the representation. Let me see where here. For example, V1 was computed here, and for what about V2? V2 was computed here this way. Exponential jp divided by 2 is simple. The j is the imaginary unit. So we have this expression. And what about V0? V0 is identically 0, and V7 is identically 0 as a representation in the space vector plane. So the output rotating vector is the vectorial combination of all these states, T1 over Ts plus V2 T1 2 over Ts plus V0 of T0 over Ts plus V7 T7 over Ts. So now we are, say, in the position to say use our assumption here, so about the position, to give say a representation of the several different states. Okay, for example, for the VU vector, which is this one, VU vector here, the rotating vector, we know that this has an amplitude, a magnitude which is alpha BD, and it has a position which is theta with respect to voltage to space vector V1. So it can be considered that cosine of theta plus P divided by 6 Pj sine of theta plus P divided by 6. Okay, so the total angle here with respect to the horizontal axis is theta plus P divided by 6. Okay, so I can get the two real part and the imaginary part that are respectively the projection along the two axes. Okay, this is, say, cosine of the angle, and this is the sine of the angle, and this is the magnitude. So this is the real and imaginary part representation of the volt of the vector VU. So let me just rewrite here what I just put there. Cosine theta plus P divided by 6 Pj theta plus P divided by 6. This is VU, and this is equal to V1, but V1 is this, so VD 1 plus J1 over square root of 3 multiplied T1 over Ts plus V2, which is, this is V1, VD 2 over square root of 3 J T2 over Ts. This is V2. Then you have the new null vectors, but the new null vectors are null, so 0 and 0. So they have no, let's say, influence on the position theta, as I said to you before. They act only on the magnitude. So let me just separate the real part from the imaginary part. So real part is alpha BD cosine theta plus, and then from this side you have VD T1 over Ts. So from this expression, it's very simple to see that T1 is equal to Ts multiplied alpha, Vd is simplified, so Vd here, cosine theta plus P divided by 6. Okay, so you can use this expression for deriving T1. This is needed for this specific theta position. Okay, so what about the imaginary part? The imaginary part means that you have alpha Vd sine theta plus 6, and it is equal to Vd that multiplies 1 over square root of 3 T1 over Ts plus 2 square root of 3 T2 over Ts. Pay attention that we already know which is T1, so I can use T1 over here. Vd and Vd simplifies, Vd here and Vd simplify. You can perform this computation, is not so difficult, I have to say. But anyway, I want to give you just the results, because T2 is given by Ts multiplied alpha sine of angle theta. So this is T1, this is T2. Which way I have to choose T0? and T7. So we have to use both V0 and V7, but typically what happens is that the time interval of application T0 is the same of T7. Remember when I said before, answering the question, that I add both the null states just for, say, increasing the symmetry of my rectangular wafer, and this may they make easier the elimination of some harmonic, high frequency harmonics in the output spectrum. Okay. In order to do that, both the time interval T0 must be equal to T7. Okay. This is exactly a consequence of my previous discussion. Okay. If we want to maximize the symmetry of the waveform, we saw something later, okay, tomorrow, that highlights and then make evident this increase of symmetry, okay, here, that both the time interval should be the same, okay, for, say, increasing waveform symmetry that is helpful to reduce higher order harmonic. Okay, so if you have that T0 is equal to T7, then we can call this equal interval T zeta, okay? Then we have that T zeta is exactly what we know, that T1 plus T2 plus T0 plus T7 is Ts, no? So that means that T1 plus T2 plus 2 times T zeta is Ts. So T zeta is 1F of Ts minus T1 minus T2. So this is the time interval in which I apply the null state. So basically I have here T1. Let me just consider starting from here. I have this expression here. As you can see, the space vector are all weighted by a fraction which is T x over Ts, T1 over Ts, T2, T0, and T7. So let me express this quantity by T1 over Ts, T2 over Ts. So I have that T1 over Ts is given by alpha cosine theta plus p divided by 6. T2 over Ts is alpha sine theta, and then you have T zeta over Ts, which is T zeta over Ts is 1F of 1 minus T1 over Ts minus T2 over Ts. Okay. So T1 over Ts and T2 over Ts has been computed here. Okay, so anytime you have a vector and you have this coefficient here, and this coefficient, what is exactly the amplitude modulation factor that I need, okay? Basically, I consider the amplitude of the vector, the rotating vector, as represented in this way, in which you have, let's say, this coefficient alpha by VT. Okay, so this exactly represents, say, the length of this vector with respect to the input supply voltage VT. Okay. Anytime you know which is your amplitude, basically, and when you know the angular position of the rotating vector in the complex plane, then you can have, let's say, you can compute T1 over Ts, T2 over Ts, Tz over Ts that you have to apply for the application of the space vectors in order to synthesize that specific position of the rotating vector. Okay, so this is this computation here, these formulas are specifically, let's say, are in a form that you can say represent in any, say, specific code stored into, say, memory of, say, microcontrollers, microprocessor, FPGA, etc., in order to make the control fully digital, for example. Okay, and so you can store this expression, and the position theta can be acquired by, say, your frequency, etc. And then it's computation that not require any analog comparison between a triangular waveform and a sine wave, for example. Okay, so this is the strength of this method for, say, modulating the behavior of the inverters and getting the three phase at the output, for example. Okay, so I will stop here. If you have questions, I can answer your questions. Tomorrow, I want to stress a little bit which is the maximum possible amplitude I can get at the output. So I will stress my explanation about this alpha coefficient I considered here. Okay, and then we can investigate a little bit about the symmetries I just mentioned before to make possible, let's say, the minimization of the dynamic power, and to, say, make possible to eliminate the high order harmonic content of the output voltage. Okay. Problems, issues, questions, whatever. Okay, thank you for your attention. We'll see tomorrow morning, 10. Bye.